Hello, everybody. I just want to go over the homework from May 6th over here. I'll go through those 3 pages of homework so you have some idea what's going on, and it'll help you with the homework that you've got due on Wednesday, which is a bunch of multiple choice, but waves don't take that long to solve. So even though it's 30-something questions, it shouldn't really be too bad. Anyway, we'll start with page 6. On the top here, this is an interference pattern. You've got your ripples coming out, and I'll put the ripples here in pink. You got a line of ripples here, line of ripples here, 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 here. Oops, missed it. Here and here. And then in between, you've got lines of no motion. And the questions were as follows. So there's our pattern there. What is it called? This whole thing is called an interference pattern. What is A called? A's got a lot of motion going on there. These are all ripples. That's an antinodal line. And what's going on, you constantly have constructive interference occurring throughout that line. Now, what's going on B, which is meant to be a line, so it didn't come out too well in the photocopy, in the scan, and that is a nodal line. There's all destructive interference going on. Now, just remember, when we did these patterns before, if I drew a line from S1 to D in this center section here, those lines are equal. There's going to be 0 wavelengths path difference down the center line. The 2 constructive interference lines, the 2 antinodal lines, there's 1 wavelength path difference between those 2. The next line is 2 wavelengths. The next line of constructive interference, 3 wavelengths apart. Now, all the nodal lines with their destructive interference, they're all off by some odd number of half wavelengths. In other words, this is going to be a half wavelength here, 1 half wavelength there. The next one is 1.5 wavelengths. And the next one's here is 2.5 wavelengths. And that's basically what we're saying is if I picked a line from S1 over here and a line from S2 over there and had all those rings that you could measure, you'd find there's 2.5 wavelengths longer path difference from S2 to that point than S1, any point on that line. So anyway, that means that S1C to S2C, well, where's C? Right over here, 3 wavelengths. S1D to S2D, well, that's 0 wavelengths because it's right there down the middle. Next one to E is right over here. That's right off from that central line, that central, called central maximum. And that's going to be 1/2 wavelength. And of course, to F is going to be 2 wavelengths. And F is right over here on that constructive interference or antinodal line. Now, sound waves are longitudinal waves. Water, at least the surface of water, are transverse. And light waves tend to be transverse also. Over here, which direction is the object moving? Well, it's pinched on the right-hand side, so X is clearly moving towards the right. What wavelength reaches B? You've got these short wavelengths right there. So B here is a short wavelength relative to what's actually being produced by the source. A, because you get this long wavelength right here, is going to get a low frequency. That's what A is going to hear. And this whole thing is called the Doppler effect. It's a shift in the wave frequency that the observer receives due to the relative motion between the source and the observer. All right, let's take a look at page 19. These are pretty much straight up calculations. They get a little dicier near the bottom, but not too bad. First one, they said a speed of an ocean wave on the coast is 42 meters per second. There's your velocity. Wavelength's 1.5 meters. Find the frequency. V equals F lambda, or frequency with VF lambda. You get 28 hertz out of that, or 28 waves per second. If the speed of sound is 340 meters per second and the wavelength is 5 meters, find the frequency of that sound and what would be the frequency if it moves into water. You got the velocity, the wavelength, solve the frequency. Frequency equals V over lambda, 340 over 5 meters gives you 68 hertz. And keep in mind, once a wave is made, the frequency never changes unless there's a Doppler shift on it. So going into water, you're going to have exactly the same frequency. Now this one, you had to read it. I know, painful. Okay, so what is the wavelength of sound emitted by a tuning fork of frequency 440 vibrations per second? Keep in mind that means 440 hertz. Okay, so the speed of sound is 332. Ooh, 332, I gotta make a correction here. 332 meters per second, sorry about that. Plus 0.6 times whatever the temperature is in Celsius. It's 32 degrees, 332. Let's make that a little neater. I misread it. Okay, 332 plus 0.6 times 32 degrees becomes 351.2 meters per second. So that means we got 351 up here. Velocity equals frequency per second. And it's going to be right around 0.8 meters. Might be 0.81 or something like that. But be right around 0.8 meters when you solve that all the way. Velocity V equals F lambda. Next one. Radio waves. I'm going to talk a lot more about radio, light, gamma, all that stuff. Radio waves travel at the speed of light, which is 3 times 10 to the 8th meters per second. What's the wavelength of a radio wave from an AM station broadcasting a frequency of 750 kilohertz? Find the frequency in meters and kilometers and compare it to some familiar objects of the same length. Okay, so here we go. Your velocity, okay, is going to be 3 times 10 to the 8th meters per second. Frequency, 750 kilohertz, or 750 times 10 to the 3rd hertz. Find the wavelength. Lambda equals V over F. You've got your velocity, you've got your frequency, that's 400 meters. You know that there's 1,000 meters in 1 kilometer, so my 400 meters is going to be 0.4 kilometers. All right, so you're talking about half a kilometer. You're talking about the length of some very large cruise ships. Very large. Okay, it's about, wrong place. Cruise ship. Or if you prefer, it could be a city block, isn't too far off from that. There's a number of things that are around 0.4 kilometers. Okay, so a standing wave, and I drew it over here on a clothesline, has 4 nodes and 3 antinodes. 1, 2, 3, 4 nodes, 3 antinodes. That means this is 1.5 wavelengths long. That's how long that is. If the clothesline is 12 meters long and vibrating 0.5 vibrations per second, okay, that's 0.5 hertz. What's the speed of the wave? Well, I know 12 meters divided by 1.5 means my wavelength is going to be 8 meters long. I got the frequency. Velocity equals frequency times wavelength. Bam, 4 meters per second. And the very last one, a wave travels from one medium to another, and the wavelength decreases. What happens to the velocity and the frequency? Well, we know the frequency doesn't change. So V equals F lambda. Frequency stays the same. No Doppler shift. I make my wavelength shorter, means my velocity goes down. All right, let's take a look at the next one here. This is page 20. You've got this wave on the top. Draw a wave with twice the amplitude. Should have the same wavelength. There's 2.5 wavelengths there. So again, I've got 2.5 wavelengths. All right. But my amplitude went from this to this. It's my rough drawing, but it's about twice what it was before. Now, a wave with twice the frequency, that means it's going to have half the wavelength. So what was 2.5 wavelengths here now becomes 5 wavelengths. 1, 2, 3, 4, 5. There it was just 1, 2.5. With twice the wavelength means I'll only get 1.25 wavelengths. So in the distance I had 2 wavelengths, I only get 1 plus another quarter. If I hit a drum and I hit it harder, I will have a greater amplitude of the wave. It still sounds like a drum, so it still has the same frequency and still got the same wavelength, but it's going to have a bigger amplitude, just like that. Now, if a pulse hits a fixed end, okay, the pulse is going to flip over on the other side. If it hits a free end, it's going to come back on the same side. If it's a less rigid medium, it acts like a free end and it's going to come back like this on the same side. Now, the next thing we talk about is superposition. These two waves occupy the same space in a medium at the same time, which means their displacements are going to add up on a point-by-point basis. Let's consider this to be 0 here, 0 here. We'll call this +1 here, -1. That's for that wave. And for this wave over here, that's +1. And down here's -1. Those would be my amplitudes. Notice all the way through here, it's 0 and 0. We've got 0. We hit this wave, it's +1. That's 0, adds up to 1. We got a little space where they don't line up anymore, and they're both 0. Then this guy goes up to +1. Then these are both at 0. This goes +1 here, just for a little length. Then that's +1, that's -1. They cancel out, and you're back at 0. Then it doesn't match on this side. It goes down to -1 against 0, so you get -1, and you're back down to 0 along the way. All right, I hope that helped you guys out, and you were able to correct what you had wrong, and will make the homework considerably easier. All right, take care now. Bye-bye.